introduction. Hello, everyone. I'm Dun Yu. I'm from University of Washington, and today I will present you the proactive sensing for improving the hand pose estimation. So everyone can hear me correctly? Okay. So let's first think of one scenario, is that when a person is trying to talk to you, but you don't really hear from this person very clearly. So what would you do? There are several options. One, you can face better toward this person. The other one, you can lean more toward this person. Or even, you use other means like your hands to help you gain better communication or improving the communication quality. So in human-to-human interaction, we have a lot of these kind of things that we proactively improve our sensing configuration, like you raise your hand to try to hear better, to improve the overall communication quality. But we also wonder, does this exist for human-computer interaction? For example, like gestural interfaces. For this kind of interfaces, it suffers a lot from miscommunication between the user to the computer. So basically, for this kind of sensor, it suffers from occlusions, for example. And for example, we have a leap sensor. It's one of the state-of-the-art sensor that you can buy from the market, and it looks for upwards to see your hands, and it tracks your fingers precisely when it works well. So basically, it still suffers from occlusions. And this kind of occlusion, in this case, it happens between your fingers. So it doesn't really necessarily tracks really well from time to time. And what about other works in the gestural sensing? So other people, they propose a lot of work about how to improve the gestural interface. Some of them, they use the multiple cameras, or some of them, they use the wrist-wearing camera or shoulder-carrying cameras. So these kind of hardwares kind of alleviate some of the occlusion issues from cases to cases. However, it still suffers because this is like a vision-based system. So vision-based system will always suffer from occlusion. Just maybe it's a more corner case or something. So we wonder, by thinking of the proactive sensing that happens in human and human interaction, can we adopt this kind of sensing techniques onto human-to-computer communications such that because we are having a proactively changing sensing platform so that we can kind of alleviate this kind of occlusion problems when communicating between the computer and a human. So we quickly built this concept proofing platform. So we built it through the Lego bricks. So up there is a IMU. So we use the IMU to know what's the current configuration of the current sensing. And we have the Lego EV3 controller as the transceiver so that we can drive the motor of this proactive platform, or we can gain the data back from this active platform. So our goal is to improve or maximize the overall communication quality in this kind of proactive platform. And in order to get the communication quality, first we use the confidence value that we obtained from the leap sensor. And we did some experiments about this confidence value. So the confidence value was derived from the model-based leap hand pose estimation. And we did some experiments to verify that the tracking accuracies are highly correlated to this confidence value. So then we use this confidence value as the surrogate for representing our communication quality. And then we build a learning system that it will proactively improve itself for the interaction. So the learning system is basically built by KT trees through approximated nearest neighbor. And we used some observations to build these trees and also generate predicted actions for the proactive sensing. The actions that are available here are, because this is a one-dimensional rotational robot arm, so the available actions are like rotating left, rotating right, or stand still. And we first generated a set of trees from our collected observation, and we use this to serve as our initial action predictor. And then when the user is interacting with the system, we will collect further observations from the user, and then we generate the online user trees for the further prediction. And later on, the new generated user tree will be combined with the base tree to do the overall prediction. To evaluate our system, we basically propose two baseline kind of sensing types. The first one is called static sensing, which means that the sensing configuration will not change with respect to the communication quality, such as the one that we mentioned previously. And the second type is called random sensing. It will be able to dynamically adjust itself, but it will just choose a random action when it's adjusting itself. And it only adjusts itself when the communication quality is lower than a threshold. And the third one is our proposed idea. So in our experiment, there are several trials. And in each trial, we will ask the user to use their fingers to grab on the virtual object on the screen for several times in a short period of time. And they will try to move this 3D virtual object around as if they are playing the game. And during the interaction, we will change the underlying sensing types for the proactive platform. And each subject will perform several of these trials for the whole experiment. And we have 17 valid subject data in our experiment. And with 17 subjects, we still got statistically significant difference comparing the improvement over the proactive sensing compared to the other two sensing type baselines. So this one that you are looking at is the overall confidence value for among all the subjects. And we also got improvement in the best confidence values that we got from all of our subjects. And also like per subject, you can see similar trends. So the conclusion is that we create a concept-proof proactive platform to prove that proactive sensing is possible to improve the overall communication quality between the human and computer. And we also propose a very simple learning system that it will learn by itself to improve the interaction over time. And the future work of this project can be, we can extend this kind of idea onto a more dimensional, more degrees of freedom platforms, such as a drone, so that you can have moving drones to interact with you, and they will try to improve the communication with you. And or you can have, for example, in the future, you might be interacting with a robot, so that the robot have to be acting like a human, so that he or she will try to proactively pose itself to interact with you. So thanks for your attention.
In your example of how people negotiate this, right, the person also sees you leaning in, and so they respond as well.
Yeah.
So I'm wondering if in your experiments you see people responding differently to the fact that this device is moving, right? So they're trying to address it, and it's also moving. And
yes. So this is something that I want to add on in the experiment setup. So we try to block the human's knowledge of seeing, of ability of seeing the hardware. So they are not able to hear or see the hardware when it's operating. So they are not being like attracted or kind of like visually like subconsciously interact with the interface. Yes.